Cool, great. Well, good morning, good afternoon, everybody, depending on where you are. My name is Jacob Carlin. I'm a research scientist at the University of Oklahoma's Cooperative Institute for Mesoscale Meteorological Studies. And today I'm going to be giving a broad overview of some projects we have that look at the synergy between using dual pole observations and one-dimensional spectral bin models and how they can apply to precipitation nowcasting. So in the polarimetric era, of course, there have been a number of polarimetric radar signatures that have been identified and that contain information about the underlying microphysical processes. And as Lisa talked about so thoroughly, we can simulate these processes using models, but they can be linked to the observations through the use of forward operators. And so when it comes to a polarimetric radar forward operator, this requires using things like particle size distributions, their hydrometeor densities, meltwater fractions, shapes, and canting angles to calculate what a hypothetical polarimetric radar would see. And this typically requires a mix of both model predicted variables, such as the particle size distributions, and then characteristics that have to be prescribed within the operator. So that includes things like shapes and canting angles, which are usually not predicted by models. So on the right here is just a quick example of the type of output we can get. This is a simulated ZDR column from the Hebrew University cloud model. So the model variables were converted to differential reflectivity, and we're able to see there that indeed we can replicate a ZDR column that is very close to what we observe. So implementing these operators alongside simple microphysical models can really do two things for us. It can help us understand what is causing a newly observed polarimetric signature, but it can also help us identify any deficiencies in either the operator or the microphysics schemes if we're unable to reproduce what we observe in nature. So over the past decade or so, this has been a popular approach. Early on, a lot of it was applied to raindrop microphysics, so things like evaporation, size sorting, and collision coalescence. More recently, we've started moving toward more complex microphysical processes, typically involving ice. So studies have taken an approach like this, looking at the depositional growth of ice crystals and things like riming. So my talk today is just going to quickly touch on 5 different sort of sub-projects we have related to snow melting, sublimation, and aggregation, and then hail as it applies to downburst nowcasting and hail swath nowcasting. And like I said before, I won't really be focused on too many of the details here. This is really just trying to highlight some of the ongoing projects we have that demonstrate the nature of this type of approach. So starting with the one-dimensional snow model, it has 2 components, of course, the microphysical side and then the radar operator side. On the microphysics side, it is a flux-conserving spectral bin model where the particles are treated as snow aggregates, although we're in the process of implementing more crystal habits. The processes included are limited to sublimation, melting, and evaporation. And the typical approach we take, and this is common to all of the work shown here, is that we initialize the environment usually from a mesoscale model like the RAP, and then we try to specify the particle size distribution at the top of the model, and then let the particles fall and simulate these processes, which are allowed to feed back with the environment. So for example, with cooling, melting, for example, we cool and moisten the environment. And then on the radar operator side of things, I typically use a modified version of the radar operator of Rishkov et al. 2011. This operator linearly varies the aspect ratio and canting angle distribution between snow and rain according to the meltwater fraction. And then for the scattering amplitudes, we use T-matrix scattering calculations and a weighted Maxwell-Garnett mixing formula during melting. So I know I kind of rushed through this a little bit. The reference below here has a lot more details about both of these things for anybody interested. Now, the first question we wanted to ask ourselves as it related to melting is what can the dual pole variables in the bright band tell us about the cooling rate within the melting layer? So with melting as well as evaporation, we get cooling and moistening. And this can really alter the local environment and have some significant consequences. This can change the precipitation phase at the surface quite suddenly, but it can also have dynamical consequences and generate things like turbulence and gravity waves. And of course, we typically lack observations of the cooling rate within the melting layer. So our general approach here was to just simulate a wide combination of different environments, both temperature and humidity, different particle size distributions of snow, and different radar wavelengths. We had 54,000 combinations in total. So I'll quickly jump to some results here. S-band is on the left, C-band is in the middle, and X-band is on the right. This top figure shows the maximum reflectivity within the simulated bright band as against the maximum cooling rate within the melting layer. Excuse me. And it's immediately apparent that there's really no good relationship here. There is a lot of scatter, and the root mean square errors are quite high. And this is actually somewhat to be expected. I know we frequently talk about bright band intensity in terms of reflectivity, but when it comes to the cooling rate, the reflectivity is really sensitive to the few largest particles in the volume, but those are few and far between typically and don't contribute to the bulk of the cooling rate. Now, if you look in contrast to the specific differential phase, or KDP at the bottom, you see a much different story here, a very constrained linear relationship between the cooling rate and KDP, and the root mean square errors here are reduced by about a factor of 5. And the reason for this good relationship is pretty much the other side of the coin, as we saw with reflectivity. When we looked at what moment of the size distribution the KDP was proportional to in the melting layer, it was proportional to about moments 1 to 1.3 of the size distribution, which is the same moment that the cooling rate was proportional to. So what this means is that it's the same size bins of particles that dominantly contribute to the KDP as contribute to the cooling rate. That results in this strong relationship. Now, moving on to some work I'm currently doing. This is regarding nowcasting of sublimating snow. So we know that if you have dry air in advance of precipitation, which we frequently see with larger systems, the dry air has to erode before snow is able to reach the surface. And this presents a really big forecast challenge, not only for when impacts begin to things like transportation, but it also affects how much snow might accumulate. So to look at this, we chose 12 cases that had operational significance where sublimation was a major factor. These are shown here on the right. These are QVPs of reflectivity, and then the contours show the relative humidity with respect to ice. So in all cases, we see an antecedent dry layer that's very deep and very, very dry. And then as snow falls into this dry layer, it slowly moistens, and snow is able to progressively reach closer to the ground, and the reflectivity gradually descends. So the question we wanted to see is how well we were able to predict when the snow would reach the surface given the significantly dry air. I'll cut to the results here. This shows the observed start time of snow relative to the model predicted start time. The red markers are the radar data. The blue shows conventional weather stations, things like at airports. And then the green data shows snowfall as reported by the general public, to kind of give us a mix of verification metrics here. But in general, we actually see pretty good performance. We have over 40% of reports were within 30 minutes of the model predicted start time, and about 2/3 of cases were within an hour. And this is coming from lead times of about 4 to 6 hours, or in some cases much more. So these are some encouraging results that indicate, if we're able to initialize this model from the observed polarimetric radar data, using these spectral bin microphysics, we are able to generally accurately predict when snow will reach the surface. The few exceptions, we had about 1 or 2 cases where the performance was markedly poorer. I'm currently still looking into this, but I believe it's due either to the particles for those cases not being well characterized as aggregates, which is how the model treats the particles, or also the role that horizontal advection of moisture might be playing, which the model currently doesn't take into account. Now, looking forward here toward how we're looking to improve the model, we're currently looking to implement both aggregation and breakup within this model. So currently, the model does not allow for interactions between bins. We treat one snowflake becoming one raindrop. This is work really being led by Lee Donovan, a coworker of mine, who is looking to study the sensitivity of the polarimetric signatures of aggregation. So we see here in this QVP, this is actually one of the sublimation cases I just highlighted, but in this highlighted period between about 16 and 20 UTC, there was very heavy aggregated snow that was reaching the surface. And the figure on the right shows the QVP profiles extracted. The median is showed in black, and then the gray shows, I believe, the inner quartile range. So we see the profiles that we often see with aggregating snow. We see an increase in Z and a decrease in ZDR and KDP downward. But we also see some more details here. Most notably, about 2.5 kilometers up, we see sort of a stagnation where the slope of the Z profile changes. And then especially the case in ZDR, where it actually becomes pretty much constant in height. And this is a signature that we also observed in a number of other cases we've looked at. So there's been prior work looking to replicate these profiles of aggregation, but a lot of them have struggled to realistically reproduce all three of Z, ZDR, and KDP. So again, similar to the results I've already shown, we initialized the model environment from the RAP model, retrieved the ice particle size distributions from the observed polarimetric data, and then invect them downward using a mass-weighted fall speed and simulate the polarimetric variables. So I'll really just cut to the chase and summarize the main results here. Overall, we are able to realistically simulate the all three variables, Z, ZDR, and KDP. We found that the stagnation point shown at about 2.5 kilometers was really due to a balance between aggregation and collisional breakup of the largest aggregates. We looked at either deposition or sublimation alone or aggregation alone, and neither of those produced realistic profiles of the variables. It was really the interchange or the interplay of all three processes that allows for these realistic profiles. We also found, perhaps unsurprisingly, that the resultant profiles were very similar to the initial size distribution of snow. So when we tested distributions that were much broader, where a lot of the mass was distributed among larger particles, the role that vapor deposition and sublimation played was really reduced, and the profiles were dominated by the results of aggregation, or the effects of aggregation, rather. So we're currently working on implementing this into the existing model that has the melting layer, as well as testing sensitivity to parameters, like the collection and breakup efficiencies. So now moving ahead to the one-dimensional hail model, this is in a lot of ways very analogous to the snow model. On the microphysics side, we simulate both graupel and hail, and we can prescribe their distributions separately. So we typically use a bi-exponential distribution. And in addition to the aforementioned microphysical processes, when it comes to hail, we also have meltwater shedding, and then the breakup of large raindrops that form from much of the graupel. And the melting model here is from the flow-dependent microphysics model put forth in Rasmussen and Hamesfield. And then again, on the radar operator side, this time we are using a 2-layer T-matrix scattering calculations, and we're treating graupel as spongy and hail as solid ice, but we're still evolving the canting angle distribution and aspect ratio according to the Rasmussen and Hamesfield model. So the first application of this is work really being led by Jordan Brooke at the University of Queensland. And he's analyzing the role that hailstone advection played in a damaging hailstorm in Brisbane, Australia, that I believe caused over $1.5 billion in Australian dollars. So obviously a very significant event. His approach is to combine a dual Doppler analysis of derived winds within the storm and initialize or initiate hailstones where he's using the hail differential reflectivity to determine where hail was located. But then once we initialize the hailstones, we use this 1D model to calculate the melting of these hailstones and their change in terminal velocity as they melt, and use that to calculate melting dependent trajectories of these particles. So I have an update pop up. Okay, so just an example of the type of things we're able to do with these melting dependent trajectories. The top figure shows the horizontal advection of 3 size categories of hail: small, large, and giant. And then even more interesting to me on the bottom, for the initialized hailstones, we are actually able to look at the impact angle of the hailstones. So we see here that small hail really comes in at a sharp angle at about 45 degrees, whereas giant hailstones fall closer to almost vertical. And that difference really has an effect on the sorts of damage that can result from these hailstones. So taking a look at some quick verification, the left here is the conventional swath without differential hailstone advection, and the right is using this new product called HailTrack. And I want to point out that the dark pixels here are where damage claims were filed with insurance companies. So this is verified using insurance claim data. And we really see overall that with the shifted swath, we really get a much better overlap with where the insurance claims are being filed. This was improved both quantitatively and qualitatively. For qualitatively, on the left here, we have the estimated maximum size of hail. We see that the largest hailstones are by and large concentrated where most of the insurance claims were filed. And then even more encouraging on the right is damage intensity as according to the normalized kinetic energy of the hailstones. But what's shaded here is the percent of insurance contracts that actually filed damage claims. And so we see really good correspondence here between where the largest amounts of kinetic energy were and where the highest rate of insurance claims were being filed. Finally, moving toward downbursts. This is work I'm doing, but it's really being led by Charles Custer, another research associate at SIMS with me. And we're really looking at the use of KDP as a downburst precursor. So we know that downbursts present really a major forecast challenge for forecasters, and this is particularly the case in low shear environments. In these environments, we find that the traditional radar metrics like descending reflectivity cores often struggle to provide enough lead time for forecasters to issue warnings. And we know from theory that the negative or the downward acceleration of downbursts is really driven by 2 things: precipitation loading and the negative buoyancy due to melting and evaporation and the cooling due to those processes. So based on this, we looked at what this 1D model of melting hail could tell us. And our hypothesis was that precip loading might be proportional to KDP, which would really mirror how KDP is used for things like QPE. And that the cooling due to melting would really be proportional to the gradient of KDP, because with melting, we're getting an increase in liquid water content, which should drive up the KDP. And so what's shown here in the highlighted boxes are the maximum KDP versus cooling rate, and then the gradient of the KDP versus cooling rate. And at least in the idealized treatment of these processes in the model, we do indeed see a good correlation here that encouraged us to look at KDP further. So based on these encouraging modeling results, we looked at 81 different downburst cases, and all 81 actually exhibited KDP cores appearing at the melting level prior to the downburst. We found the maximum correlation at a lag of 3 volume scans. So the KDP was really leading the observed divergence in the radial velocity by about 10 to 15 minutes. So that was very encouraging as a tool, but where it became a bit more challenging was using the KDP to actually forecast downburst intensity. There was really a lot of overlap in the distributions. And what we found, which in hindsight really makes a lot of sense is that the environment really matters. We know that certain environments are more favorable for downbursts. And when we separated the cases into favorable environments with steep lapse rates and unfavorable environments, we really saw what is driving this. If you look at the unfavorable environments, the violin plots here show the distribution between strong and weak downbursts. Compared to the favorable environments, we require higher KDPs to drive a downburst. And this makes sense. If the KDP is indicative of the precip loading and the cooling, for an unfavorable environment, we're going to require more precip loading and more cooling to overcome the unfavorable environment. Whereas the favorable environment, we actually had lower values of KDP. And then within these environments, once you partition them, higher values of KDP did tend to result in stronger downbursts. So while this might be tricky to use in real time due to the overlap between the distributions, we believe that such an approach can be used to kind of triage which storms really require a forecaster's attention when you have a situation where many storms are present. So I'll quickly wrap up here. The goal of this talk really was to just demonstrate the potential of these types of 1D models coupled to forward polarimetric radar operators and the types of value that they can provide for insight into microphysical processes. So with the SNOW model, we've found insight into the relationship between latent cooling and the brightband signature and the melting layer, as well as nowcasting the erosion of dry air due to snow sublimation. And then the HAIL model has really yielded some insights into which polarimetric variables may be useful for downburst nowcasting, in this case KDP, and then helping to improve hail swath trajectories. So going forward, we're still making improvements to the SNOW model. I mentioned that aggregation is currently being interfaced alongside the existing model of melting. We would like to eventually extend this to both nucleation and rhyming to really have a full column model where we're able to kind of extend the distances over which we're able to do comparisons. So we'd be able to look at, say, the characteristics of the PSDs in the dendritic growth layer up around -15 degrees, and then correlate that with the resultant brightband signatures or the types of resultant precipitation rates or rain rates at the surface. But with that, I will wrap up, and I'd be happy to take any questions anybody has.
Okay. Thanks to you. Thanks, Jacob. And yep. There is one question by Clemens.
Okay.
Clemens? Are you muted? Otherwise, I also can read your question. Okay, so maybe I will read it now. And he asked, or he says, the 1D model and the forward operator show very good correspondence with observations. Do you plan to simplify the 1D model so it could be used in NWP in order to enable the direct assimilation of polarimetric radar observations?
Yeah, that's a really good question. I haven't yet worked toward directly simplifying things. Obviously, as mentioned by previous speakers, the efficiency of both the model and the operator is really of utmost importance when you're looking at things for assimilation. And so, for example, right now we're using T-matrix scattering. That's really not obviously going to be able to be implemented in a real-time system where time constraints are a concern. But we do hope to, especially with aggregation, the aggregation process is very computationally intensive. But we hope to be able to develop, at least some better insight into the parameterizations using the detailed scheme and the operator to then maybe develop simplified relations that can be used in more bulk microphysics models. But yeah, that's a really good point.
Okay, thanks. I hope this was fine for Clemens.